So I welcome you to the second lecture of group theory. This is lecture 2. Let me recall what we have done in the lecture 1 and then we will move to lecture 2. In lecture 1 we have defined the binary operation. Then we defined groupoid. Then semi-group, and then semi-group with identity, that is also called the monad. This is what we have done, and then we define group, and we have done some examples of group. In example 1, we find that z plus set of integers with respect to addition, set of rational numbers with respect to addition, set of real numbers with respect to addition, and set of complex numbers with respect to addition is a group. And next example 2, we have shown that the set of rational numbers minus 0 is a group with respect to multiplication. Similarly, R star with respect to multiplication, and set of complex numbers star means complex numbers minus 0 with respect to multiplication is a group. And then in example 3, what we did in example 3, we defined as one circle group, that is called circle group, and this is the set of those complex numbers such that mod z equal to 1. And this is again a subset of set of complex numbers C, and this is a group with respect to multiplication of complex numbers. So S1 with respect to dot of complex numbers is a group. This is what we have done. And next example was example 4, in which we define the set, perhaps I denoted by P, and this was those z in C such that z to the power n is equal to 1 and n belongs to n. We are calling it the roots of unity. So again, this set P with respect to dot is a group. You can see that this is a subset of complex numbers. So complex multiplication is here. Identity 1 will be here because that will be the some roots for some n. So this is a group which you have seen in the last lecture. Now come to the next example. So now we are beginning with our lecture 2. So now example 5. So from here we are starting this lecture 2. So nth root of unity. Nth roots of unity. So nth root of unity, what is that? So fix a n in n, or take any integer, positive integer or natural number. So define a set Pn to be those z in C such that z to the power n is equal to 1. This is again a subset of set of complex numbers. So because associativity is there with respect to multiplication for whole complex set, so associativity is there in this set. 1 is always a root because 1 to the power n is 1, so 1 belongs to Pn. So 1 will work as a multiplicative identity because if you take any z in Pn and you will multiply it by 1, then you will get z itself. So 1 is there. And inverse is also there. Why? because if you take any z in Pn, then 1 by z to the power n is equal to 1 by z to the power n. This is also 1. So this implies 1 by z belongs to Pn. So z into 1 by z is equal to 1. So inverse of z is, so z inverse is 1 by z. So Pn is a group with respect to multiplication. So this Pn is a group. Now what is, you can say that what is the difference between P and Pn? So one can see that, for example, if I talk about P1, that is one root of unity. So there is only one number such that 1 to the power 1 is 1. If we talk about P2, then 1 minus 1, second root of unity you can say. And if you talk about P3, then it is 1 omega square. Means third root of unity, and omega, you know, omega is the root of the equation 1 plus x square. Similarly, if we talk about P4, then what is P4? P4 is 1 minus 1 I minus I, and so on. And what is P? P is actually union of all these P's. So that is the difference between P and Pn. So what is P? P is actually union of Pi. I is varying from 1 to infinity. That is the difference. So P is the group that is called the root of unity. So it contains all the roots of unity. And this is for fixed n. Pn is the nth root of unity. So both are good with respect to multiplication operation. Now we are coming to the example number 6, and that is group of integers modulo n. So to understand it, this is modulo. Okay, so understand this, let me fix a positive integer n in n. Now for m in z, in any integer positive, negative, 0, we denote m modulo n modulo n by m bar, and m bar is defined as follows. So what we do? We fix an integer n in n. I choose any integer m in z, and now I am going to define what is m modulo n. So it is usually denoted as m bar, and the definition of m bar is now as follows. Because m is any integer, we can divide m by n. We will get some quotient, and at last we will get some remainder by doing some steps. So m can always be written as q into n plus r. This r is a remainder, and you know remainder is always positive or maybe 0, and is always less than n. Then m bar is r. In some books it is also written as r bar. So both are same thing, either you write r or r bar. So but actually m bar is r. So integer modulo m modulo n means r. That can also be written as r bar. Okay. For example, suppose I take n is equal to 5 and m is equal to minus 2. So m is any integer and this was a natural number. So by m bar we mean the remainder. So we need to first determine the remainder. So what we will do, we will divide minus 2 by 5. So how many times will it go? Minus 1 times. So you will have minus 5. This will become plus. So it will become 3. So we can write m means minus 2 as minus 1 times 5 plus 3. So this is our r and this is our q. So it means minus 2 bar means 3. Some people also write it as 3 bar. Both are same thing. And that is because when you will determine the 3 modulo 5, then you will again get 3. 3 modulo 5 means 3 itself. So that's why 3 bar is also 3. So people are writing this as 3 or 3 bar. So this is m bar is equal to, we will simply write it as 3 or 3 bar, whatever you want to write. Okay. So now suppose I choose n to be 5, then when you will go on determining the modulo of all the numbers, then the only possibility of modulo is the number of remainders you are getting after dividing by 5. So you have only 5 possibility, that is 0 or 0 bar you may write, 1 bar, 2 bar, 3 bar, 4 bar. So when you will take the modulo of all the numbers, all the integers with respect to n is equal to 5, then you will get only 5 numbers, and these are the remainders which you will obtain after dividing the number by 5. Okay. So we usually denote this set as Z5. And similarly, if you will determine it for n, then Zn means 0 bar, which represents actually those integers which when divided by n will give you 0 remainder. 1 bar, 2 bar, 3 bar, and similarly n minus 1 bar, because these are the only possibilities of remainders. Okay, so this set Zn is we will show that it will form a group with respect to addition of these numbers. We will define addition, and that is called the group of integers modulo n. So let us define addition operation on this set. So define an operation plus from Zn cross Zn to Zn as x bar plus y is defined as, suppose I take two numbers here, x bar and y bar in Zn, and now I am defining how to add these two numbers. So what we will do is that we will add these two numbers and take modulo n. So again it will be in Zn, so clearly it will be in Zn. So here x bar, y bar belongs to Zn. Now this operation is also associative. Why? Because suppose I take x bar, y bar, z bar in Zn, then we can define x bar, let us check it. So by definition of addition, we can write it as x plus y whole bar plus z bar. Now again, by definition of addition of these two, we can write it as x plus y plus z whole bar. Now this is the addition of integers which is associative, so we can write it as x plus y plus z whole bar. So clearly, now by the definition of this bar or modulo, we can write it as x bar plus y plus z whole bar, and this can again be written as x bar plus, now y plus z whole bar means y bar plus z bar separate. So it means this operation is associative. Now as we know in Zn there is one number 0 bar. So if I take any number x bar in Zn and I add it with 0 bar, then by definition it is x plus 0 whole bar, and that is same thing as x bar, and that can also be written as 0 plus x whole bar, so 0 bar plus x bar. So it means 0 bar is an identity element. This is an identity element. One more thing is that suppose I take x bar in Zn, then n minus x bar also belongs to Zn, because bar of any number just belongs to Zn. So what will happen? N minus x bar plus x bar, if we will do, this is n minus x plus x whole bar, this is n bar, and n bar is 0 bar. So it means inverse of x bar is n minus x bar. Is it okay? For example, let me do it for n is equal to 5. For example, if I take n is equal to 5, so we have z5, and I take 3 bar in z5, then this n minus x means 5 minus 3 bar, that is 2 bar. This is also in z5. So when we will add 3 bar and 2 bar, then we will get 5 bar, and 5 bar is nothing but 0 bar. So this is working, and this is same thing as 2 bar plus 3 bar, again you will do, then it is 5 bar, so it is 0 bar. So the inverse of 2 bar, so if I am writing inverse like this, is 3 bar, and the inverse of 3 bar is 2 bar. So the inverse exists, identity element exists, associativity is there, so it means Zn with respect to plus is a group. This is a group, and this group is called the group of integers modulo n. Now we can define one more operation on this set, and that is the multiplication. This addition is usually called the addition modulo n, and in some book you may get it is written like plus n because it depends upon n, and in some books you can see it like this. So symbols does not change mathematics, definition is same, notations may be different. Okay, so let us also define one more operation, and that is the operation of multiplication modulo n. So define multiplication from Zn cross Zn to Zn as x bar dot y bar. This is defined as x into y whole bar. So what we will do? We will first multiply x and y and then put bar on it. For example, for n is equal to 5 in Z5, if I take two numbers, suppose I take 4 bar and 3 bar, and I want to multiply it, then we have 12 bar. So we will divide 12 by 5 and we will get the remainder 2, so it is 2 bar. So it means this multiplication is a binary operation on Zn. Let us check the associativity of dot. Associativity of dot, then okay, so take 3 element is in Zn, then x bar dot y bar dot z bar. Let us check it. So by definition of multiplication, x bar dot y bar is xy whole bar dot z bar, and by definition of multiplication again it can be written as xy dot z whole bar. But this is the multiplication of integers. So multiplication of integer is associative, so we can write it like this. So we can write it as x bar yz whole bar, and this is x bar y bar z bar. So it means Zn dot is a semi group because this operation is associative. So it is a semi group. Now, as you know, in Zn there is an element 1 bar in Zn. So when we will multiply 1 bar with any x bar in Zn, what will happen? This is 1 into x whole bar, that is x into 1 whole bar, you can write it like this. So that is actually x bar, which you can simply write it as x bar into 1 also. So it means 1 bar is identity element with respect to multiplication modulo n. So this dot is called multiplication modulo n, and 1 bar will work as identity element for this multiplication modulo n. Now this means that Zn dot is a monad. Now the thing is it a group? So the answer is no, it is not a group, because 0 bar does not have an inverse. Why? Because we will not get any number x bar such that when you will multiply it with 0 bar you will get 1 bar. So it is not possible, because 0 bar dot x bar is 0 into x whole bar, that is 0 bar. So that is never equal to 1 bar. So this is not true. So So 0R has no inverse. No inverse with respect to this multiplication. So it means this is not a group. So Zn dot is not a group. This is not a group.